Hey folks, welcome. We are taking a look at Unit T, two sample tests of means. And we're going to be looking at using Excel's analysis tool pack as well as the ANOVA template. So let's take a look at an example here. Now I'm using the Business Admin survey data, and this is found in the supplementary files folder. It's the data set that I used in the data cleaning labs. So it looks like this. This is the clean data. And I'm going to make a copy of this, working on this particular sheet. You'll also notice that I've made a copy of the file itself here. So I'm not working on the original data. Let's take a look at an example here. I want to look at the relationship here between gender and height, which should be a fairly obvious one here. So I'm going to get rid of the columns which are not gender and not height. Fortunately, they're together here. I'm going to keep the respondent number, and I'm going to get rid of all the rest here, like so. All right, remember that it is a good idea here to keep the respondent number because there are no blank cells in the respondent number. And so you can sort these three columns together even if there are some blank values. I don't think there's any blank values here, but let's just go and check. I'm going to sort by height, and it goes from 141 centimeters down to 198 centimeters. So we're good. I'm just going to get rid of this blue line here. And then let's do the same here then for gender. And we've got the females, and then we've got the males. And oh, there is an N at the very bottom here, which stands for neither. And so in our write-up, we certainly want to mention that, but there won't be enough here for us to be able to do statistical comparisons. So we're going to get rid of that and just leave us then with the male and the female heights here. All right, next thing I'm going to do then is to unstack these variables. So I've got the gender variable, which is nominal, and I've just sorted according to it. You'll notice that I have a shaded line here just when I'm doing sortings to make sure that they sort together, and they do stay together. So we know that the heights were also sorted according to the gender here. So now I'm going to go over here to the top, and I'm going to put in female and male, and I'm going to go and grab the heights that correspond to the females here. So I'm going to copy that, and I'm going to paste that down here. Let me go up to the top here and paste those. And then I'm going to go down here then to the males and grab their heights. So these correspond to the M's. And there we go. And I'm going to copy that and then paste those guys. So I've got now the female heights and the male heights. They won't necessarily be the same length, and that's actually fine. Not a problem with that. All right, now one thing to note here is that we need to check to see if these are normally distributed. And I want to show you what we would use for that. So if you go over here to the one-way ANOVA test here, and I'm using the ANOVA template, so you'll find this also in your supplementary files folder. What we do is we highlight these guys, so the two unstacked columns, including the titles at the top. So I'm just going to copy those, and I'm going to move over here to the ANOVA template, and then right in this cell right here, the orange cell, I'm going to right click and choose Paste Special Values. All right, that is useful here. It actually runs this as an ANOVA test, but we want to look at this as a two-sample t-test. So One of the conditions here is that the data are normally distributed. So let's go down here to the Normality tab. And in the Normality tab, what we've got is the following here. Now, the null hypothesis says that the data from the ith treatment, so we've got 2 treatments, one for females and one for males, are normally distributed. So it's actually 2 separate normality tests here. And so we take a look here, and then we take a look here. If we end up rejecting HO for either one, then we have a problem with normality, except that if the n's are at least 30, then you don't have to worry about it because of the central limit theorem kicking in. So it's just like the flowchart that we went through at the end of our first stats course and the beginning of this stats course here, the review questions. Then if n is at least 30, you actually don't have to worry about the results of the normality test because the central limit theorem kicks in. So although this particular one here says reject HO, we don't have to worry about that because n is at least 30. All right, if this were, of course, less than 30, then you would have a problem here in that you're rejecting HO, so normality would not hold for the males if you had a low n. And that means that we could not do a t-test for the differences of means. We would actually have to just go to the Kruskal-Wallis results, which is over here in the tab, and use these guys instead. Remember, the Kruskal-Wallis test converts the interval variable into ranked values. So these heights, of course, are interval in nature. It's an interval variable, classified according to the 2 nominal treatments, gender, female and male. So that's what we would do there. I'm going to get back to this particular ANOVA page here later. Actually, I'm not. I'm going to continue on here and say, then what we would do is we could go over here to where it says the homogeneity of variances. And the homogeneity of variances, you only go to this particular tab if normality passes. But normality was not a problem because each of the n's were at least 30. So now we go up here and we say, what have we got here? The Bartlett's test for homogeneity of variance has a null hypothesis that says that the variances of the treatments are equal. And in our case, we reject that. So that means that we should be using a t-test for unequal variances. On the other hand, if the Bartlett's test says that we do not reject HO, then we can use a t-test for equal variances. It also turns out that the t-test for equal variances gives you the same results as the ANOVA test. And I'm going to get back to that a little bit later. But in our case, what we did was, again, we unstacked the variables here. That was the first step. We put them into the ANOVA template and then turned to normality. Normality is not a problem because the n's are at least 30 for each one. So you don't worry about the results of the Anderson-Darling normality test. So now we go to homogeneity of variances, and here we reject the HO for the Bartlett's test. By the way, don't worry about the Levine's test here. So we're just going to be using the Bartlett's test here. The Bartlett's test depends on normality, and we don't have a problem with that because of the size of our n's. So that means that we should be using a t-test assuming unequal variances. What we do then is we go into data analysis, and remember this is the add-in pack, so you can add this in. There's instructions how to do that in the supplementary files folder. This is where we saw descriptive stats, and we saw ANOVA, and then down at the very bottom we've got our t-tests. So there's the t-test for matched pairs, which is one of the types of tests. You're probably not going to use that for your particular project. You're likely to use one of these 3. The t-test assuming equal variances, actually we don't even have to use that because the ANOVA results give us the same results. Okay, but this is the guy that we will use, and then this one is a z-test, which we'll get to in a moment. Okay, so this is the guy that we will use where it says the t-test to sample assuming unequal variances. Now this is really easy to set up. As long as your data are unstacked, put into separate columns here. So we've got the female heights. That's going to be your variable 1 range. Your variable 2 range will be your male heights. We always put in a 0 here, at least for the problems that we're looking at in our class, because we'll always be testing the null hypothesis that the mean height of females is equal to the mean height of males. And so, in other words, the difference between the two, we're hypothesizing to be 0. And we'll always do it that way. Check on the labels button over here. Choose your alpha. It defaults to 5%. And then press select your output range. So I'm going to just scroll back up here to the top and choose the cell and press OK. And let's take a look at how we would read this. I'm going to make this a little bigger so you can see this. And these are the results that we end up with here. So okay. And I think what I'm going to do is I'm going to take these down to about 3 decimal places or so, just so that they're a little easier to read. Oops, there we go. All right, so what we end up with then is that the mean height from the sample shows that the females are on average 166 centimeters and the males are 177 centimeters. And that is a significant difference here. If we're taking a look then at females minus males, because the first variable was females, so females minus males, the difference then when you put it into the T formula is minus 5.390, which is way, way out there in the left tail. This is a two-sided test, so we would be comparing it to a critical value here of 1.992. The degrees of freedom are kind of goofy. They're 76, but that's because there's that complex formula that is used to calculate the degrees of freedom. You'll never have to actually do that, but it's a complex formula. You'll only have to do this with the computer for the t-test assuming unequal variances. The p-value is, it's hard to tell in this particular case here, but this p-value here of 0 is actually twice this one. So if I was to take this to several decimal places, you would actually see that the two-sided p-value is twice this guy here. So in our particular case then, we would say, well, we've got a p-value here then of 0, and of course that is less than 0.05, and so that means that we're going to end up rejecting HO, or whatever your alpha is, right? It doesn't have to be 5%. That would of course change the critical value if it was different from 5%. Regardless, that means that there is a significant difference between the two, and if you go to the top you can see that the males are on average significantly taller than the females. So we would copy and paste this output and put that into a Word document and add your hypotheses, your conclusion based on the results, and you're done. Now, while we're here, what I like to do is to show you that if we went to, let's go back to the Data tab. If this were a problem where we were given the population variances, then this would make it a z-test. And the Z-test then is set up almost exactly the same way. So I'm not going to actually run through this, but you would put in the females here, you put in the males here, the difference would be 0, and then whatever the hypothesized variance is for each one. So if I said that the hypothesized variance was, say, 25, then I would stick that in here. That would be for, say, the females. And then for the males, let's say it's, well, I'll just make it 36. Of course, if you're given standard deviations, then you need to square those and put those in as the variances. Of course, the variances could also be the same, in which case you would put the same number in each of those. And then you just continue on. Everything else is exactly the same. You choose labels, your alpha value, and your output range, and you would end up then with Z values over here. So you'd have a Z statistic, and this would be 1.96 as a critical value. And so that's the difference between them. So I'm not going to actually go through and do that because it's an easy fix there if you're given the standard deviations or variances of the populations. What I would like to do, though, is to show you one more example here. And let's go back to our clean data here. And the reason why I want to show you this one here is that I want to show you how you handle these kind of questions here, which are the check one only kind of questions. So let's make a copy of this data. Right there. And what I'm going to look at here is there a difference here between the pulse rate of those who use sports facilities versus those who don't? So I'm going to get rid of everything except for the pulse rate here. And then these guys over here, I'm going to leave. Now, this particular question here was, which of the following have you frequented at RDC in the last month? And so, or have you used at RDC? So the food services, the far side, the document center, and the sports facilities right here. Okay. So that is all one question, but it's a check all that apply. So how do you use that in analysis? Because we might want to compare this to, say, the pulse rate. Now, it's probably more likely that we would compare this to something like age, or we would compare this to gender or something, but I thought it might be interesting to check this against the pulse rate, because often people will say that, you know, the athletes have slower pulse rates on average than the non-athletes. The unfortunate thing with this question is that all it said was, have you used the sports facilities? But so it might be a good idea to find out their frequency of use. Are they just a casual user? Do they just use it once? Or do they really, are they the athletes that tend to use it quite a bit here? So the question probably could be a little bit better here. But regardless, I want to show you how to handle these check all that apply questions. So in this particular question then, people were asked to check up to 4 values here in terms of which of the different RDC services they have used in the past month or so. What I always do in this particular case then is I'm going to set up a new column. I need to give it a title at the top here because I'm going to do some sorting. So you need to put something in. I'm just going to call it the count because that actually is what I'm going to be using here, is the count across. So you notice this adds up to 2. Let me just make that font a little bit bigger here. Go to the home tab here. Okay, so this is a count of 2, and I'm just going to go all the way down here. Of course, I'm going to sort these guys, so I might as well color that orange, like that. And so this particular person then checked 2 of the boxes, and this particular person actually checked 4 of the boxes, and so on like that. This is assuming that you have already cleaned the data. And so there's no X's or words in here or anything. There's just numbers. 1 if they have selected it or checked it off, and blank if they haven't. All right, now this goes all the way down here. What I'm going to do now is I'm going to sort according to the count. So let's go and do a sort. And what that does then is it puts the zeros at the very top. Why is that important? Well, because these 3 people here didn't actually choose anything, so they didn't answer the question. So we only want to keep people who actually selected one of the values here. They actually answered the questions here. Now, by the way, that doesn't necessarily mean that they didn't answer the question at all, but we can't tell here. It might be that they haven't used any of these. And so it would probably be a good thing to put down as an option in this question that they've used none. And then find out how many people actually used none. But I'm going to get rid of any of the people here who didn't check off any of these. So really what we're looking at is people who have used some of the facilities at the college. So let's get rid of these. And now you can see that the counts go from 1 down to 2, 3, and finally up to 4 there. Okay, let me just get rid of this blue line here. Now that's a handy kind of thing to do. I can now get rid of that count column there. By the way, of course, you should also go to the pulse column and you should do a sort there. And just make sure that there's no blanks here. So it goes from 52 down to, there is a blank here. So we're going to get rid of that particular row there, because that person didn't give their pulse rate. So what we're left with now is that everybody has answered the question as to what their pulse rate is per minute, and then they have selected at least one value here. All right. Now, what do you do from this point? Well, what I'm going to do here is I'm going to highlight these cells here all the way down, and this is for question 14, which is asking them to check all that apply. And I'm going to do an edit, and then I'm going to do a find and replace. And in the find and the replace, there's a couple of ways that I can handle this. Is I could change all the ones to yeses and all the blanks to nos. And so let me just start you off and show you that. So I could say find a 1 and change it to the word yes, and then replace all. And you see what happens there is it changed all the ones to yeses here. I'm actually going to undo that here. I'm going to show you just changing them to 1s and 0s. That's going to be handy when you get into some of the other stuff that we'll be doing. So the next video we'll look at proportions, and they need to be 1s and 0s. And then when we get into multiple regression, we'll have something called a dummy variable, and that has to be classified as a 1 or a 0. So I've got them all highlighted, and I'm going to go back into edit and then find and replace. And I'm going to keep the ones the way they are, but the blanks, and to show a blank, actually, I just simply put nothing in there. So find nothing and replace it with a 0. And so then I replace it, and it says it's made 137 replacements, and that is great. Okay. Close. Good. All right. Now, so that's how you handle this kind of thing. And then in our particular case, we want to just take a look at sports. So what I'm going to do here is I'm going to delete the other columns here. And that's going to leave me now with pulse and then sports. Now, what is common here is to name the one. And so in this particular case, then we would actually just call it then that they use the sports facilities versus not using the sports facilities. So if this, for instance, was gender and you had ones and zeros, whatever the ones were, you would call them by, you would rename the variable not gender, but male or female, depending on what you coded as ones. So that's how we tend to handle that. That will come in handy later when we're looking at these other kinds of problems here. So now what we've got here is that this actually is still a nominal variable. It's a yes or no. And then this here is the pulse rate. So what I'm going to do then is I'm going to break that into two treatments. So I'm going to sort here. And remember that the we've got yeses and nos here. Let's make those a little bigger, like that. And the no's actually corresponded to the zeros. So I'm going to take the pulse rates that corresponds to the no's, or the zeros. I'm going to copy those there. Let's try that again. There we go. So I've pasted those. And then I'm going to come down here then to the where the sports equals 1, which meant yes. And, oops, should have done that a little differently there. Okay, so these are the ones corresponding to the ones. And I'm going to grab those guys. Did I get them all? Yeah, okay. So copy and paste here. Good. So now what I've done here then is I have unstacked the pulse rates according to whether they've used the sports facility or not. Okay. And I could still keep them as ones and zeros, but you just have to remember what the ones and zeros stand for. So this is yes to sports, no to sports. All right, let's go over here to this one-way ANOVA thing, and I just need to clear this out from the last problem that we were working on. Okay, so you open up your ANOVA template and make sure it's all blank here. And I'm going to go and grab these guys. And I'm going to copy them. And move over here to the here. And I'm going to paste that. Good. All right, so I've got the yeses and nos, and now I'm going to go over to the normality page. Now, is there a problem with normality? Well, the answer, first of all, is no, we don't even have to look at this because the n's are at least 30. And even if they were less than 30, it looks like we end up not rejecting HO anyways. So an n less than 30, we would still be passing normality here. But this is what you want to look at. Each of these n's are at least 30. So normality is good. Central limit theorem kicks in. We move on to homogeneity of variances. The homogeneity of variances here says that the Bartlett's test, the null hypothesis is that the variances are equal, and we do not reject that hypothesis. So that means then that the variances are equal here. Now, let's go back here and take a look then at the t-test assuming equal variances. So I've got data analysis, and it says the t-test 2 sample assuming equal variances. Okay, my variable 1 range is going to be my yeses all the way down here. My variable 2 range will be my no's. My hypothesized difference is 0. That's what it will always be. My labels in my first row, choose my alpha, and then my output range. Remember, with a t-test, you don't input the variances. So this is assuming equal variances, but it's still calculating the sample variances and using those in the formula. So it does that internally. You don't need to actually input any variances like you would in a z-test. But our Bartlett's test told us that there is no difference in the variances, no significant difference. So we're going to come up here then and just put in the output range, and let's see what we end up with. Now, let me just clean this up a little bit right here, and I'll take it up a little bit more here. And so we end up with something that looks like this. All right, so the mean differences between them then is those who use the sports facility have an average pulse rate of about 77 beats per minute. Those who don't, it's 75 beats per minute. Here's your T statistic, and it's pretty low. We would be comparing that to a critical T value right here. Alternatively, we could use the p-value, and that p-value, of course, is 58%. That is not less than an alpha of 5%, so we do not reject HO. So either way then, whether it's the classical approach comparing the T star to the critical T or the p-value, we would not reject HO. But I want to show you one other thing, and that is that, as I mentioned, you never really have to do a t-test 2 sample assuming equal variances, because the results that you get from ANOVA are the same. Let me show you. So I'm just going to go and grab the output here. I'm just going to grab this part right here. Okay, I guess I should probably take the title too. And let's just move back here and see what we end up with. So these are the ANOVA results that we get. And maybe what I'll do is I'll put it beside it instead. Okay, that's going to be a little better. Oh dear, you know what? Sorry about that. Let me just back up here. Okay, there we go. That's better. That's cleaner. And what I want to show you here is, if you take a look at the means, and let me just get rid of these guys right here. The means here of 76.87 and 75.29 are exactly the same as we get up here, right there. Okay, look at the p-value. The p-value here, let me give us a different color here. That p-value of 58.2% is exactly the same p-value as we get right here. So the p-values turn out to be exactly the same. If I square this guy, so that's equals that squared, I get 3.97, which actually is the critical value for the f-test. So if you square the critical t value, you'll get exactly the same critical value as for the f-test. And if I take a look at the t star formula, and if I square that, I end up with 0.307 or 0.31, and there it is right there. So that's interesting to note that. Remember that an f-test is looking at a ratio of variances. Variances are squared numbers. So these guys that we get right here, and maybe I should take them down to a couple of decimal places so you can see them a little better. So the t star squared is exactly the same as the f star. The t critical squared is exactly the same as the f critical. And the p-value, not squared, the p-value is just the same, is exactly the same as the p-value right here. You get the same means and everything else. So what that's saying here then is that if you're using this ANOVA template to test the normality and the homogeneity of variances, which you need to do to find out whether what t-test you're going to use, if you end up with a t-test assuming equal variances, you actually don't even have to do that because the results are right here. So I think that's exciting anyways. That's one of those cool stats things. So that is where I want to end this particular lesson here. We've taken a look at the t-test for means, assuming unequal variances and equal variances. And then I briefly talked about the the z-test. So if we were giving the population standard deviations or variances, and we would stick those into the input box. And we're not going to talk about the matched paired problems. We're not going to do that particular one here. And if you run into that on a project, then we can certainly talk about that individually. That will leave one more video that I'm going to do on proportions. So let's stop this guy here, and thanks for watching.